Welcome to BCIS 3347. My name is Dr. Schuessler, and today's topic is Chapter 2, Networking Standards and the OSI Model. So the objectives for this chapter are to be able to identify organizations that set standards for networking. So there's a lot of different organizations that work together to be able to develop these standards to make sure that various components interoperate, hopefully seamlessly. And so we'll talk about some of those organizations. We'll describe the purpose of the OSI model and each of its layers. It's a 7-layer model that is really kind of a de facto standard in the networking field. It's really more conceptual in nature. There are more applied models, but it is really kind of the grandfather, if you will, of networking models. And so that's the one that the book really follows along pretty closely. We'll explain specific functions belonging to each OSI model layer. You should be able to understand how two network nodes communicate through the OSI model. We'll discuss the structure and purpose of data packets and frames. And then we'll describe the two types of addressing covered by the OSI model. So before we jump into some of these standards making bodies, what is it that they do? Well, obviously they create standards. And what is a standard? It's a documented agreement. It basically says this is how our devices are going to operate, and so this is how your device, a different manufacturer, can make products and services that will interact with our devices, and they can communicate back and forth hopefully seamlessly. So it stipulates design and performance characteristics of a particular product or service. Standards are important particularly in the networking world, because we have lots of different manufacturers all over the world that are manufacturing these various devices, whether it be switches or routers or IP cameras or IP phones, lots and lots and lots of different devices. And what allows them to be able to communicate without having problems are the standards that they're adhering to. If they didn't adhere to those standards, we tend to have a lot more problems than what we have now. So it ensures network compatibility. Standards define a minimum acceptable performance level. So in other words, we're not saying that these devices will perform a lot better. Hopefully they will, but this says all the devices that meet a particular standard will perform at least up to a minimum level. Now, when it comes to creating standards, there's lots and lots and lots of different organizations that all work together and kind of have created their own little pieces of the pie that help to make all the various components that we have work together. So some examples are ANSI and IEEE, but there's lots and lots of others out there, and we'll talk about several of them over the next few slides. It's important for you to have kind of a general understanding of some of these networking standards making bodies, but it's also important to have a little bit more in-depth knowledge about ones that are really more specific to your little niche, whatever that niche may be that you kind of carve out for yourself. So the first one is ANSI. That's the first one we're going to take a look at, the American National Standards Institute. Lots of different representatives, both from industry and government, and they help to determine standards for the electronics industry and other fields. Compliance is voluntary with those standards. In other words, there aren't no ANSI police. They're not going to come out and get you if you don't comply. But they certainly issue those standards, and they have a pretty rigorous testing process to be able to meet ANSI approval. And those standards can be found online, which is really kind of what they want. They want organizations to be able to see what those standards are so that they can develop products and services that will comply with them. A couple other popular ones, EIA and TIA. The Electronic Industries Alliance is a trade organization, representatives from U.S. electronics manufacturing firms, and they help set standards for their members. They also participate in writing ANSI standards, and they help to lobby for favorable legislation related to computers and electronics. The TIA, Telecommunications Industry Association, is an EIA subgroup that merged with former U.S. Telecommunications Supplier Association. And the focus of the TIA is to develop standards for information technology, wireless, satellite, fiber optics, telephone equipment, And you see some of their standards, for example, if you're familiar with creating networking cables. that there's a few standards that are out there that tell you exactly what color wire goes to which pin on your RJ45 connector, for example. So some of these should look familiar to you if you have been in the business for a bit. Another big one is the IEEE, the Institute of Electrical and Electronics Engineers, an international engineering professional society, and their goal is really to promote the development and education in electrical engineering and computer science fields. So they do a lot of work. They don't only help to set standards, but they also produce a lot of conferences, technical papers, academic papers. They meet regularly to be able to help hammer out a lot of understanding and agreement for various standards and improve education, things of that nature. The ISO, the International Organization for Standardization, is a collection of standards organizations from a variety of different countries around the world. And the goal of the ISO is to establish an international technological standards to facilitate global information exchange and barrier-free trade. So the idea is that we can develop our standards to really allow us to operate globally rather than focusing just in Europe or just in the United States or just in Asia. We want to be able to eventually get to a point where our communications equipment and devices work regardless of where you are in the world. So it's pretty widespread authority. The ITU is similar to the FCC here in the United States, the International Telecommunications Union. It's a part of the United Nations, and they help to regulate international telecommunications. They really focus on developing countries and helping them with technical expertise and obtaining equipment. It's been around for a very long time, founded in 1865, and you can see that quite a few member countries as well. The Internet Society is a professional membership society, establishes technical internet standards, and their primary concerns currently, and there are things that are changed over time, but their primary concerns currently are growing the internet, particularly in developing countries, keeping the internet accessible, in other words, making it so that people with low income can still be able to afford and access necessary resources on the internet. Information security, a stable internet addressing services, and open standards. ISOC also oversees groups with specific missions, such as the IAB, the Internet Architecture Board. And this is an advisory group that really kind of oversees the Internet's design and management on a really more of a daily basis. The IETF, Internet Engineering Task Force, helps to set Internet system communication standards, especially protocol interaction, the different layers that have to communicate. Anyone can submit a proposal, and then it goes through a process of reviewing it, testing, approval processes, etc. A couple of ones that you may have heard of are IANA and ICANN, and they both deal with IP, Internet Protocol Addresses. And so we'll talk about this more in later chapters, but IP, or an Internet Protocol, is an IP address, is an address for identifying a specific host or specific device on a network. And it really relies on a centralized management authority to be able to dole these out to specific individuals. It's the logical address that's assigned to individuals, and that's where IANA and ICANN come into play. So IP address management historically was managed through IANA, and they were the ones that ran that. And IANA is still around, but their role has changed around. In '97, 3 RIRs, Regional Internet Registries, were ARIN, APNIC, and RIGHT. And in the late '90s, ICANN came around and essentially took over part of the function of IANA. So it's a private nonprofit corporation, and they maintain the responsibility for IP addressing and domain name management, whereas IANA performs system administration. So IANA is still around, just their role has changed a bit. Users and businesses obtain their IP addresses from their ISP. Okay, so now we're going to shift from talking about some of those standards making bodies to one of the really kind of main standards or models, if you will, when it comes to networking, and that's the OSI model. The OSI model is not the only model that's out there. There's a variety of other models that are out there as well. The Internet model, the DoD model, sometimes there's a lot of similarities between some of the models, a lot of overlap. But the OSI model is one that's been around for a very long time, and most people tend to point to it, and this book certainly follows that. And the Network Plus exam focuses on the OSI model as well. So before we jump into it too much, keep in mind a model is a representation of something that is actually exists. So it's a simplified version. It's something that's easier to look at and kind of pick up and look at from different angles and observe, but it's not all of the detail of the actual phenomenon that you're looking at. So the OSI model was developed in the early 80s, and it divides network communications into 7 layers. So physical, data link, network, transport, session, presentation, and application. So that's going from the lowest level layer, physical, to the highest level, which is application. If you look at this in reverse from the top down, an easy way to remember this is all people seem to need data processing. So these are 7 layers, and they all interoperate with one another. So how does that interoperability actually occur? Well, how do these different layers interact with each other? With the exception of the top and bottom layers, each layer interacts directly with the layer above and below it. The application layer interacts with the software that's above it, the software that we actually deal with as users, and the layer below it. The physical layer interacts with the actual cables and connectors, and then the layers above it. So again, as a model, it's a theoretical representation describing network communications between 2 nodes. So it's representing how that data traverses the protocol stack in one system, across the wire, across radio waves, across fiber optics, to a receiving node, and then back up the protocol stack on that receiving side. It's hardware and software independent. Doesn't matter whether we're talking about Cisco switches, that type of stuff. It doesn't matter about the brands, the Dell servers, HP laptops. Does not matter. It's completely independent of hardware and software. Every network communication process must be represented, and something that you'll hopefully get used to is this idea of protocol data units, which is really more of a generic term of segmenting the data, of breaking up data into smaller chunks or discrete amounts of data and into smaller, more manageable chunks that can be used by lower level layers. We'll talk about application layer functions and how the data flows through the various layers in the next few slides. Again, it's a model, so it's not perfect. It's not going to be completely descriptive of exactly how the data flows, but it does give you a pretty good idea. So this is what it might look like. This is one way of trying to represent that data flow. So say we have a client here on the left-hand side and we have a server on the right-hand side, and you make a request for, say, Google over here on the left-hand side. You type www.google.com into your address bar on your client over here. That software application, not to be confused with the application layer, the software application passes that request to the application layer, in which case, in this particular case, the HTTP protocols used at that layer is going to accept that request and start passing it down through the various layers. So we're going to go through the presentation layer, through session, through transport, through network, through the data link, to the physical layer, which is going to translate it into 1s and 0 pulses, electrical pulses if we're talking about copper wire, or light pulses if we're talking about fiber optic, or radio waves if we're talking about wireless. So we're going to send that data across our network medium until it gets to the protocol stack on the server side. And that data is going to travel up the data side to Google servers. Google servers are going to say, oh, I've just received a request for our Google homepage, and it's going to respond with that information. And we'll see the whole thing happen in reverse. So that top layer is the application layer. Like I said, this is not to be confused with the software application that we might be interacting with. This is referring to the application layer of the OSI model. So it does not include software applications. The function of the protocol at the application layer is to facilitate communication between the software applications, so in our example, a web browser, and the lower layer network services. It helps the network interpret application requests, and it helps application interprets data sent from the network. So it works in both directions. Software applications negotiate with the application layer protocols by formatting, processes, security, synchronization, and other requirements. And as I mentioned, HTTP is a common protocol used at that layer. There's lots of protocols that are used at that layer. So for example, FTP is another common application layer protocol. So here's what it looks like in trying to build this model and flesh it out a little bit more. We have our software application here, which is a web browser, which through APIs interacts with the application layer of the OSI model using the HTTP protocol. The next layer down is the presentation layer, and the functions of this protocol are to be able to accept information from the application layer of the OSI model and to format data. This is what allows different systems on the internet that don't necessarily speak the same language to still be able to communicate. So it allows us to serve up a GIF or a JPEG or a TIFF, for example, from, say, a Linux server to be viewed on a Macintosh machine. So this presentation layer is what allows us to be able to do that. Presentation layer also services manages data encryption and decryption, so SSL, for example. So again, here's an example of how this might look like. We've got our web browser that interacts with the application layer through APIs using the HTTP protocol, which interacts with the presentation layer using SSL, TSL, or TLS, etc., to be able to encrypt and decrypt layer information. The next layer down is the session layer, and its job is to coordinate and maintain communications between two network nodes. In other words, it opens up a connection and keeps that connection open for as long as it needs to be kept open. This is why when you go to, say, for example, a bank website, you log into your bank account online, and then you're able to navigate from page to page to page, conducting your business. You don't have to constantly log back in. The way that's done is your state is being managed, your session is being managed. So it's a connection that has been created using the session layer to be able to do that. So the functions of the session layer are to establish and keep alive a communications link, keep communications secure, synchronizing dialogue between two nodes, determining if a communications transmission is ended, terminating communications, setting the terms of communication, and identifying session participants. So another example might be an internet phone call using an IP phone. So you set up that initial request for the call, internet phone B replies back, says, okay, go ahead. Well, in the middle of a conversation, while you are talking for parts of it, there are also parts where it's silent. But you don't want that connection to close when the line goes silent. You want it to stay stay open, stay part of that connection, keep that connection open. So this protocol would continue to test the connection and say, are we still open? Are we still going? Are we still communicating? And as long as both sides are still sending that information and still receiving a still here type signal, that connection is going to stay connected until a request is actually sent to end the call and the other side agrees to it. Now those top three layers really, for the most part, tend to get treated as a single layer. Most software applications kind of roll those three up all into one layer to deal with them. For example, most of those functions are all built into a web browser. A web browser handles presentation and session. and application layer issues. So that's why you see in some other networking models, such as the Internet model or the DoD model, those tend to be treated as one layer. But the OSI model does differentiate them, and you really should be aware of them for test purposes. The transport layer is the next layer down, and the functions of this protocol are to be able to accept data from the session layer above it, to be able to manage end-to-end data delivery, and to handle flow control. So the transport layer's job is to make sure that data leaves the sending side and is actually received on the receiving side. And then it handles flow control, so the speed of the data. In other words, one side may be really fast, but if the receiving side, the sending side may be really fast, but if the receiving side is really slow, doesn't have much in the way of memory to be able to hold data, the sending side needs to be able to slow down, to slow that flow down so that the receiving side can still receive that information. When we talk about the transport layer, generally we have two types of protocols, or two classes of protocols. We have connection-oriented protocols, and we have connectionless-oriented protocols. A connection-oriented protocol sets up a connection on both sides before communication occurs, and this is done using a three-way handshake. Through a handshake uses a send packet initially, then you end up with a send ACK and then an ACK. And that's what establishes the communications between two different nodes. TCP uses this approach. As far as making sure that the data that is sent is actually the data that is received, some sort of a checksum needs to be calculated. And oftentimes this is done, it's a calculation that's done on the data that's sent, is sent along with the packet, and that calculation is rerun on the side where it's received. And if those two calculations equal each other, we can assume that the data has arrived intact. On the connectionless side of things, a connection is not established before data is sent. Rather, a best effort is made. We send out our data packet and we hope that it's going to be received at its destination. There are reasons why we might want to do this. This UDP uses this, for example. There are reasons we might want to do this. For example, when we're dealing with video conferencing, we want a connectionless protocol because it tends to perform much more efficiently. Because it doesn't have the additional header information, it tends to perform much more efficiently. More of the packet can be dedicated to the actual data, rather the actual payload, rather than the rest of the overhead. In other situations, we need to make sure that all of the data is actually intact and we don't end up with any corrupted information. So, say, for example, an email that has a file attachment. If part of that file is corrupted, we may not be able to use any of that file. So TCP may be a better choice. In some cases, messages are much too large to send across as an entire message, as a whole file. So in those cases, we might want to break that up. And that's where segmentation comes into play. It breaks up larger data units from the session layer into smaller, more manageable chunks called segments. And this can also increase our data transmission efficiency. And it does this because, say, for example, we have a very large file that we want to send across a network. If we send this entire file across and part of it is corrupted when we do our checksum, we've got to retransmit that file. Well, if we had broken it down into smaller chunks, the only parts we would only have to retransmit the parts that were actually corrupted. So segmenting can actually save us in terms of efficiency. Related to this is the maximum transmission unit, and this defines how big those segments can be. Now, if we're going to break messages up into segments, we need some way of reassembling those segments together into a message that makes sense. Especially when we're talking about UDP or something like that, we need to be able to put those segments back together in a very specific order and make sure that, because they may go different routes. So we do that through some sort of sequencing where we're going to tag each segment that goes out with a sequence number, and then we can reassemble them on the receiving side. So say, for example, we have a message, and This is obviously not a very long message, but let's assume for a second that it is a long message, and that we want to break it up into each individual character representing a message. So when we do that, we essentially are going to tag each one with a 1, 2, 3, 4, so we know which order they go back into the network to be reassembled on the receiving side. So let's say on the receiving side we receive 3 first, and then 4, and then 2, and then 1, and then 5. Well, now we know, because they're numbered, we know which sequence that they actually go into to be reassembled on the receiving side. So here's an example of what a TCP packet might look like, some of the information in that packet. We have our sending port or our source port, our destination port, our sequence number, acknowledgement number, length, etc. So a lot of information in there. The next layer is the network layer, and the functions that operate at this layer are the translation of network addresses into their physical counterparts. And it also decides how to route data from the sender and the receiver. It does that through addressing. Addressing is a system for assigning unique ID numbers to network devices. So when you see that, you should be thinking in your mind Internet Protocol, IP addresses. So a couple of types of addresses that are discussed here in the chapter. There's actually more than this, but the ones that we're talking about specifically here are network addresses, which are logical addresses, and physical addresses. So at this layer, we're talking about logical addresses, network layer addresses, such as an IP address 10.34.99.12. That's a logical address. It's something that we assign to that particular computer. It's unique to the network. It can't be duplicated anywhere else on the network. If we do, we have a problem. So it's a unique logical address that we've applied to a particular workstation or server or some other node on the network. A physical address, such as 006097-3E97F3, is a hexadecimal representation of binary, and it's an actual number that's not assigned to a specific computer. Rather, it's a hard-coded address for a network interface card. I say it's not assigned. There are some unique situations where you can actually assign your own network MAC address or hardware layer address, but for the most part they're set by manufacturers, and so we don't have control over those numbers. There are a number of factors that are used to determine how the packets are going to travel across a network. Some of those are priority of delivery, network congestion, quality of service, and cost of alternative routes. And so a router will make decisions based on how we're going to set these various characteristics, delivery, priority, network congestion, etc., and determine the best route to send a packet to make sure that it reaches its destination. And routers are used for that purpose. So by far the most common protocol at this layer is the IP protocol. Fragmentation is similar to segmentation. It's the idea of dividing layers or dividing packets up into smaller, more manageable pieces. Hopefully at this layer we don't have to do that, but it is something that can be done if need be. For the most part, you don't have to worry about that. The protocols take care of that for you. Here's an example of what the protocol looks like itself, what's going on in the packet itself. So we've got our source address, an IP address, the destination, where it's going, which version of IP is being used, 4 or 6, the length of the header, etc., etc. The next layer down is the data link layer, and the function of this protocol is to divide data received into distinct frames for transmission in the physical layer. So this is down at the local area network. Up until this point, we've really been dealing with more the WAN environment, a larger scale environment. Now we're down to the local area network environment, and we still have this need to be able to break up larger transmissions into smaller, more manageable transmissions to be handled on the local area network. So at this layer, when we break them up, we're talking about a frame rather than a packet or a segment. So we're talking about a frame, and this is a structured package for moving data. So it includes our payload itself, which is the actual data that we're interested in, as well as the sender and receiver's network addresses, error checking, and all that kind of stuff. At this layer, we certainly have issues with communications. Not all information may be received, so there may be a need to retransmit, for example. And we do that. We identify those issues by checking for errors. There's different ways to check for errors. There's frame check sequences, there's CRC checks. There's a number of different ways of checking for errors, but essentially they all work off the idea that there's some sort of mathematical calculation done on the sending and receiving messages, and if those numbers match up, they're felt to be intact. The message is deemed to be intact. One of the possible issues here is a possible glut of communication requests, where the data link layer so the data link layer needs to be able to control the flow of information to be able to make sure that a NIC doesn't get overloaded with data requests and start having all kinds of errors. Within the data link layer, there's actually two sublayers, the LLC and the MAC, the logical link control sublayer and the media access control sublayer. And they each perform related functions. They work together to be able to perform the data link layer functions. So the MAC sublayer manages access to the physical medium. So it's what actually deals with working on the actual physical medium, like the wire, or putting the electrical pulses onto the wire, putting the light pulses onto fiber optic, or the radio waves into the air. The physical address is a fixed number associated with each device's network interface. So this is oftentimes why you hear it referred to as a MAC address or physical address. It's done by the manufacturer usually, and it's unique to each network interface card. So the data link layer might look something like that, where it's one layer, but it's split into these two sublayers. So we just got through talking about media access control. The logical link layer provides common interface, reliability, and flow control. So it manages that flow of messages to the layer above and to the media access control layer to make sure we're not putting too many ones and zeros, too many electrical pulses onto the wire at one time that wire might not be able to handle. So here's an example of a wireless access card, a network interface card that might be plugged into a desktop computer. In a lot of cases, they will have the MAC address imprinted on them so you can read them. In other cases, you can see them in the software. You can certainly run some network diagnostics and see the MAC addresses of your network interface cards in the operating system that you're using. But again, these tend to be unique and are set by the manufacturers. There's a few examples or a few situations where that's not always true, but for the most part, that's a given. Okay, now the last layer of the OSI model is the physical layer. And the functions at this layer are to be able to accept frames from the data link layer, so that layer above, and generate signals as changes in voltage at the NIC. So we've got several different types of mediums that are typically used: copper, fiber optic, and wireless. Copper is certainly the most common, or has been the most common for a very long time. Unshielded twisted pair and shielded twisted pair, they're relatively inexpensive. They perform well. They're good choices in general. Fiber optic is becoming more popular. It is, however, expensive, so that's why it doesn't tend to be used as much. You can't work with it quite as easily, but it does give you some additional security, and it certainly performs quite a bit better in terms of speed. And then we've got wireless, which is becoming more and more popular every day. It seems like it uses radio waves, has its own limitations in terms of range and things like that, but certainly the speed aspect of wireless has come a long way and is very competitive with a lot of copper transmission mediums. Some of the physical layer protocols responsibilities when receiving data are to detect and accept signals. So be able to accept those signals, to pass data onto the data link layer, to set the transmission rate, that flow control issue, to monitor data error rates, but there's no error checking at this layer. The devices that operate at the physical layer tend to be hubs, repeaters, and switches, with switches really being the most common at this layer. Hubs you're really not going to see anymore. Be a pretty rare situation in which you did. NICs operate both at the physical layer and the data link layers. So here's kind of a nice summation of those different OSI levels. There's the application layer there at the top, presentation, session, transport, network, data link, and physical. So again, all people seem to need data processing. And then it gives you a nice summation of the functions of those different layers. So be sure and take a look at that. You might want to print it out and kind of walk around with it for a while until you get it pretty well memorized. It's certainly something that will pay dividends, especially if you're not that familiar with networks and you want to get into networking. This is stuff you really need to know pretty well, pretty thoroughly. You don't have to know the nitty-gritty of it, but you want to have a general idea of all of these functions. So communication between two systems. Well, essentially you've got the issue of data transformation. So the original software application data differs from the application to physical layer of data. In other words, it doesn't look the same traveling all the way through those different layers. Information is added at each layer, and we'll have a graphic here in just a little bit that will kind of show you some of that. So we have PDUs that are generated in the application layer. Segments are generated in the transport layer. Packets are generated at the network layer, and then frames are generated at the data link layer. So what happens is we have this process that's referred to as encapsulation. That's where we take the layer that's above it and we encapsulate it into a frame or some sort of data unit below. And we add some additional information to that, whether it be IP information, transport information, or whatever. And we'll see that here in just a second. So encapsulation occurs in the data link layer. It's the process of wrapping one layer's PDU with protocol information, allows the interpretation by the lower layer. The physical layer transmits the frame over the network. So the process of encapsulation looks something like this. At the application, at the software application layer, which is up here all the way at the top, we're going to type in our address. We're going to type in www.google.com. When we do that, that request, www.google.com, becomes our data. That's our payload. It gets passed on to the application layer of the OSI model. So that's our payload. Well, we end up with application header information, application layer header information that's tacked on to that, and then all of that is passed down to the next layer, the presentation layer. So to the presentation layer, this is our payload. This entire bit here is our payload for the presentation layer. The presentation layer encapsulates that and tacks on its own header information. Same thing happens at the next layer, the session layer. The session layer encapsulates all of that and adds its own session header information, and so on, and so on, and so on. So we go through this process of encapsulation. On the flip side, we go through a process of decapsulation where we start pulling those back out to get down to our original payload. So frame specifications. Frames are composed of several smaller components or fields, and frame characteristic dependencies really depends on the network type, so where the frames come from and how they work and all that, and the frames, the standards that frames must follow. In other words, different standards that operate at this layer are not interoperable. In other words, if we have token ring and we have Ethernet, they don't communicate with one another. The construction of the frames are different, so they can't communicate back and forth. Ethernet is by far the most common protocol at this layer. It's been around for quite some time at this point. It's developed originally by Xerox And while there's 4 different types of Ethernet frames, the most popular is definitely 802.3 and 802.11. 802.3 is wired Ethernet. 802.11 is for wireless. The competing standard is Token Ring, which was developed by IBM and relies on direct links between nodes and is configured in a ring topology. It's nearly obsolete. There are very few situations where you might run into something like this. It's not interoperable, as I mentioned, with Ethernet, so it's something that it has really died out. Token Ring was historically more expensive than Ethernet. Ethernet was always relatively inexpensive, performed well in most situations, so Ethernet ended up dominating in this field. So Ethernet frames and token ring frames differ. They won't interact with each other. They won't talk to each other. So you can't have a computer with a Ethernet card talk to another computer with a token ring card. It won't work. In order to kind of be able to keep track of all these different Ethernet standards, IEEE's Project 802 was an effort to standardize physical and logical network elements, and so that's the 802 project's role and responsibilities. And so they address issues such as frame types and addressing issues, connectivity, networking media, checking for errors with various algorithms, encryption, as well as other various technologies. And they're the ones that are responsible for, like as I said, 802.3 and 802.11 for Ethernet and wireless, respectively. So again, here's kind of a nice little table to break some of those down. And it's important to kind of have a general idea on most of these, but the ones you really want to focus on, particularly for test purposes, is 802.11 and 802.3. So to kind of sum up this chapter, standards help to ensure interoperability between software and hardware from different manufacturers. This is what allows us to go out and buy different computers with different network interface cards, different switches, different routers, and expect all of those devices to be able to communicate with one another. We also talked about the ISO model, or ISO's OSI model, and how that represents kind of a generic or really kind of a bird's eye view of how data traverses a network. So we talked about the different layers of the model and how data moves up and down those protocol stacks. We talked about the 802 project from the IEEE and how its goal is to standardize network elements. And we talked about some of the 802 standards, specifically 802.3 and 802.11 for Ethernet and wireless. And if there are other ones that are out there, there's lots of other ones, but those are the 2 that you probably really want to focus on for exam purposes. So that is all I've got for you today. That's it for Chapter 2. If you have any questions, send me a message and follow me on Twitter at Schuessler PhD. Check out some of my other social networking sites, YouTube, etc. And let me know if you have any questions. Take care.